Thank you so much, and welcome to the session on carbon dioxide removal, and thank you for joining us. Before we start, I would like to note that today the initiatives Strike for Black Lives, Shut Down STEM, and Shut Down Academia are calling on the research community to reflect on systemic racism and the action needed to eliminate it. The journal Nature is supporting this important initiative today, so publication of today's issue has been delayed, and most day-to-day activities have been stopped to reflect and think about what actions we can take to tackle systemic racism. Nature was invited to curate today's content for the research stage, and we decided to continue our participation in today's event after some discussion. And our aim is to spotlight exciting research that we are seeing in our journals. So now returning to the topic of today's session, so the aim of the Paris Agreement on climate change is to pursue efforts to limit global warming to 1.5 degrees Celsius above pre-industrial times in order to prevent some of the worst effects of climate change. At present, cuts to carbon emissions are not big enough and they're not happening fast enough to achieve this aim. In fact, in order to deliver on the ambitions of the Paris Agreement, the Intergovernmental Panel on Climate Change presents illustrative future pathways that rely on the removal of carbon dioxide from the atmosphere. And there are concerns that there's a disconnect between the role that carbon dioxide removal is envisaged to play in keeping global temperature rise below 1.5 degrees and the reality of implementing the removal technology in time and at scale in the real world, with many technical, financial, and regulatory challenges still to be overcome. So this is what we are to discuss: to what extent we can rely on carbon removal to limit global warming, the technology options available, and obstacles to overcome. And we have a fantastic panel to discuss it with, and it's my great pleasure now to introduce our very distinguished speakers. So we have Heleen de Coninck, who's a full professor in Socio-Technical Innovation and Climate Change at Eindhoven University of Technology, and an associate professor at Radboud University. An atmospheric chemist by background, her research now focuses on international climate policy and innovation. She is currently a coordinating lead author in the Intergovernmental Panel on Climate Change, or IPCC, 6th Assessment Report on Mitigation, and she was a coordinating lead author in the IPCC Special Report on Global Warming of 1.5 degrees. Before joining academia, she worked at the Energy Research Center of the Netherlands for over 10 years. Welcome, Heleen.
Thanks.
Our second speaker is Pete Smith. He's Professor of Soils and Global Change at the Institute of Biological and Environmental Sciences at the University of Aberdeen and Science Director of the Scottish Climate Change Centre of Expertise. His interests include climate change mitigation, soils, agriculture, food systems, ecosystem services, and modelling. He's a Fellow of the Royal Society of Biology, the Institute of Soil Scientists, and the Royal Society of Edinburgh. He's also a Foreign Fellow of the Indian National Science Academy, a Fellow of the European Science Academy, and a Fellow of the Royal Society. Great to have you here, Pete. And our third speaker is Cameron Hepburn. He is Professor of Environmental Economics at the University of Oxford, Director of the Smith School of Enterprise and the Environment, and serves as Director of the Economics of Sustainability Program at the Institute for New Economic Thinking, Oxford Martin. He has published widely on energy, resources, and environmental challenges across many disciplines, including engineering, biology, philosophy, economics, public policy, and law, drawing on degrees in law and engineering and masters and doctorates in economics. He has co-founded 3 successful businesses and provides advice on energy and environmental policy to national governments and international institutions such as the United Nations. Thank you all so much for being here. Heleen, would you like to start us off, please?
So indeed, Heleen de Coninck, Technical University of Eindhoven. Can you please share my slides? Thank you. So I'll just start with my key points, and they're basically based on the IPCC special report on limiting warming to 1.5 degrees, which was written in response to a request from the parties of the Paris Agreement to explain the difference between the impacts at 2 degrees of warming compared to pre-industrial times and 1.5 degrees of warming, and also to look at the different pathways and what are the differences in actions that need to happen between 1.5 and 2 degrees of warming. So some of the conclusions were that basically limiting warming to 1.5 degrees has very clear benefits. So preventing the worst of climate change, including the completely going extinct of coral reefs, possibly much more sea level rise, really requires limiting warming to 1.5 degrees. We also concluded that it's still possible to limit warming to 1.5 degrees, but it requires very fast and unprecedented changes, especially unprecedented at scale. We also concluded that if you want to be on a mitigation pathway that limits warming to 1.5 degrees, this requires system transitions as well as carbon dioxide removal. The models that make these calculations, they basically don't solve unless there is some part of negative emissions or carbon dioxide removal, especially later on in the century. However, the extent of the use of carbon dioxide removal depends very much on other action, and I'll say a little bit more about that. And then I'll just go into some conclusions of very preliminary research work. We haven't even submitted it yet, which is really on when carbon dioxide removal is carbon dioxide removal, and also when carbon dioxide capture and utilization can classify as carbon dioxide removal, because sometimes there's some confusion on that. So this is a graph from the 1.5 degrees report. It is in the summary for policymakers. And on the x-axis, you basically see time up to 2100. And on the y-axis, you see the global emissions of CO2 in gigatons or billion tons of CO2 annually. And if we focus on the blue lines, the blue envelope of lines, those are the ones, the pathways of emissions that give us a reasonable chance at limiting warming to 1.5 degrees over the course of the century. So that over the course of the century, the temperature doesn't sort of go over 1.5 degrees briefly and then big dip back under again. The gray scenarios have a high overshoot, so they go over 1.5 degrees, but still have a 50% chance or so that at the end of the century, the temperature rise is limited to 1.5 degrees. And basically, there are three key characteristics of these pathways. They halve global CO2 emissions in 2030 compared to now. The CO2 emissions in 2050 are net zero, so essentially we don't emit any CO2 anymore globally, so not just in developed countries, but globally. And any CO2 that still is emitted is compensated by negative emissions or carbon dioxide removal. And practically all scenarios have some degree of carbon dioxide removal later on in the century. So remember this sort of pathway, right? The form of this graph. Now it's clear that those kinds of changes, and we're talking about 7% CO2 emission reductions per year for the next 30 years in order to make this happen, to limit warming to 1.5 degrees. This really is a huge challenge. And we're really concluding that this cannot be done by implementing just a list of technologies. This needs to be done by systemic changes. And we have 4 areas of systemic changes. We need system changes in the energy system, in land and ecosystems, urban and infrastructure systems, and also in industrial production systems. Now, my presentation now is very brief, so I cannot go into all these systemic changes, and I'll really try to focus on the topic of today. If we take 2 out of these, spaghetti lines that you saw in the diagram there, then we can explain how it works in terms of that early action can prevent a greater extent of carbon dioxide removal later on. And this here is essentially the same graph, but only one of the lines. And the gray part is the positive emissions by fossil fuels and industry. The brown part is positive or negative emissions by agriculture, forestry, and other land use, which Pete will talk more about. And the yellow part, which is not shown here, but you'll see it in the next graph, is carbon dioxide removal by a technology called bioenergy and carbon dioxide capture and storage, which combines carbon neutral bioenergy with the capture and geological storage of CO2, so it leads to a net removal of CO2 from the atmosphere. And this is a scenario, this P1 scenario. They call it low energy demand scenario because of early action in terms of reducing energy demand. You see a fairly rapid reduction here, and then you don't need as much of carbon dioxide removal towards the latter part of the century. You maybe need a couple of gigatons, a billion tons of CO2. In most of the scenarios, however, that picture looks very different. This is another example where we see that basically we keep on emitting through fossil fuels and industry much longer. So we basically build up a much bigger carbon debt, and then we need to go negative much more, and then we'll end up with the need to remove carbon dioxide from the atmosphere through bioenergy and CCS, or maybe through other means. The models are not yet that sophisticated in this case, so many carbon dioxide removal options are not included. But that would have to be at more than 10 gigatons of CO2 net removal from the atmosphere in the second half of the century. And just to put things on perspective, currently we are putting 40 gigatons of CO2 into the atmosphere. A quarter of that or something would have to be removed from the atmosphere. So the challenge of that is enormous. Now, this is a more complicated graph. What we try to do here is really look at what are the criteria for mitigation technologies to be sort of compatible with Paris. And this is particularly relevant in the scope of this carbon dioxide utilization group of technologies. And we basically said two things. If you follow, again, that rough shape of the curve that we saw earlier, and we need to halve emissions in 2030, then any technology that is Paris compatible must be able to at least halve CO2 emissions compared to what currently happens in 2030. Also, we need it to be ready for use then, so it cannot be too early in the development stage. If it's currently a lab idea or just an idea in an inventor's mind, it will not be ready in time for commercialization in 2030. Innovation just doesn't happen that quickly. And that's why we introduce sort of a condition here. Not only do emissions need to be halved, also the technological readiness level needs to be at least 6. That's a level of demonstration. And then it's usually still another 10 years or so until a technology can be implemented in the market. If we look at 2050, we can give ourselves a little bit more time for maturing technologies. We say, well, there's basically not a limit for that. But obviously, the emission reduction criteria is stricter because basically we need net zero CO2 emissions. Now, if we apply that to different technologies, and that's what we're going to do in a paper which still is to be submitted, then we can sort of categorize technologies into whether they are Paris compatible. But very importantly, this needs to be done over the complete life cycle of the technology. Now, just to close with 2 more slides, the question is, when is carbon dioxide removal really carbon dioxide removal? When is it actually valid to be given that name and to be playing that role basically in achieving the Paris Agreement? First condition is obviously that physically greenhouse gases need to be removed from the atmosphere. And they need to be stored out of the atmosphere in a manner intended to be permanent, or at least for a very long time. We need to take account of full life cycle greenhouse gas emissions, both upstream and downstream, and they need to be comprehensively estimated and also included in the emission balance. And the total quantity in that life cycle of atmospheric greenhouse gases removed and permanently stored has to be greater than the total quantity of greenhouse gases emitted to the atmosphere over the entire life cycle. Again, now that goes for carbon dioxide removal options like bioenergy and carbon dioxide capture and storage. If your biomass is grown sustainably and is not leading to too many greenhouse gas emissions as you are recovering the biomass, but I'm sure Pete will go more into that. If you apply it to carbon dioxide capture and utilization, we can see how that applies, and maybe we can even in the discussion go into a couple of examples of that. Basically, we're seeing that CCU can only be carbon dioxide removal if atmospheric or biogenic carbon is used. Otherwise, you would be using fossil carbon, and basically you're not removing anything from the atmosphere. Secondly, the gases need to be stored out of the atmosphere. However, that is usually not the case for carbon dioxide utilization. They're often used in, or that's the plan, to use them in fuels, which like methanol, which you would combust again, and then the CO2 would be released again. However, for enhanced oil recovery and also for construction materials, you could say that might apply. You also, well, again, you need to look at the full life cycle, and this also includes emissions from energy using capture and conversion, and also re-emission of CO2 through degradation, etc. So this excludes EOR, enhanced oil recovery, actually, and implies the need for very low or zero emission energy, like nuclear energy or renewables. And we need to look at the total quantity of greenhouse gases, so not just compare the CCU emissions to the conventional products emissions, but look at the absolute amount of emissions. So with that, I'll close. I hope I stayed sort of in time, and I look forward to the discussion. Thank you very much.
Right, Heleen. Can I hand over to Pete, please?
Yes, thank you very much for inviting me to speak here. My name's Pete Smith. I'm at the University of Aberdeen. And what I'll do in my presentation, short presentation, is I'll just whiz through some of the various options that are available for carbon dioxide removal. So can you please start sharing my slides? That's great. So there are a number of technologies or options available for carbon dioxide removal. The first group of them are natural, and you can see over on the right-hand side of the screen, they're listed here: afforestation, reforestation, biochar, soil carbon sequestration, and other land use, for example, wetland, peatland restoration. All of these take place in the land-based sector, and they're all sort of things that we pretty much know how to do. For example, we've been planting trees for thousands of years. We know how to do that. On the right-hand side of this figure, it shows some technological measures, options that could be used for removing carbon dioxide from the atmosphere. I'm going to cover direct air capture and accelerated or enhanced weathering today. I'm not going to include ocean alkalinity enhancement, and I'm not going to include carbon use, the CO2 into durable carbon. Heleen's already mentioned that, and Cameron's going to cover that in more detail. But sitting between the two, the natural and the technological based solutions, there is one that's been mentioned by Heleen already. That's bioenergy with carbon capture and storage. So what I'm going to do today is go through each of these one by one, just with one slide each, just to explain how they work. The first one is afforestation, reforestation. So basically this is just planting trees or creating new woodlands. So what happens here is you plant trees, and they, through the process of photosynthesis, they fix carbon dioxide from the atmosphere into the tree. So as the tree grows, in the biomass of the tree, carbon is accumulated and it's taken out of the atmosphere. Some of that carbon coming in from photosynthesis is lost with the process of respiration, but some of that carbon is fixed in the plant as it grows. You can see trees getting bigger every year, and that's carbon dioxide being stored from the atmosphere. And some of that carbon accumulates in the debris and in the litter and is stored in the soil. So afforestation is planting trees to remove carbon dioxide from the atmosphere, and it's stored for a period of decades. Maybe longer if you use the wood products in long-lived products like buildings and such like. But that carbon dioxide is locked up in the atmosphere at least for decades, so they can contribute to net zero by 2050. The second option is soil carbon sequestration, and this works by stabilizing carbon in the soil. So when carbon is added to the soil, it undergoes some changes. Some of it's lost through soil respiration as CO2, but some of that soil carbon is stabilized in the soil, and again, it can last for a period of decades up to centuries. So maybe of the amount that you put in, maybe about 10% is stabilized. So you can increase the soil carbon either by increasing the organic inputs, so that's measuring your residue, managing your residues better with organic amendments, increasing plant inputs, maintaining plant cover, deeper roots, and those sorts of things. Or you can reduce disturbance, so that reduces the carbon losses. So you can restore and re-wet farmed organic soils, and you can reduce other losses, for example, through changing tillage practice. So that's creating a carbon sink in the soils that's locked up for a period of decades. The next technology is biochar. So what you do is you take biomass either from crops or from trees, and it undergoes a process of pyrolysis. And what pyrolysis means is just burning the biomass in an oxygen-limited environment. And you end up with biochar, as shown here on the right. It's a very sort of stable material, which you can then add to the soil, as shown here. And this lasts in the soil for anything from decades up to centuries. So you can stabilize the biomass into a stable form and apply it to soils where it locks up that carbon that would otherwise be going back to the atmosphere. The next one is peatland restoration, wetland restoration. Peatlands store twice as much carbon as all the world's forests. A lot of people don't realise what an important carbon storage they are. They cover only about 3% of the land area, but they store about 30% of the global soil carbon. And in many areas of the world, peatlands have been drained for various purposes, generally agriculture and sometimes production forestry. But you can re-wet those soils, and it prevents large CO2 losses, and it also encourages long-term carbon sinks. So as it's photosynthesized, the peatland grows, and it's taking carbon dioxide out of the atmosphere. That covers the natural-based solutions, the one based on the land. I'll just talk quickly about a couple of the technology-based solutions now. The first is direct air capture with carbon capture and storage. And this relies on passing the atmospheric air over a reactor, and which is a fairly low concentration of CO2 in it. But you then absorb the CO2 onto sodium hydroxide or amine, two reactants that you can put in that absorb CO2. You then remove that CO2 from the amine or the sodium hydroxide, and you can then pump that underground into geological storage, either solid as a basalt, or you can put it into depleted oil and gas reservoirs or saline aquifers for storage. So this is a technology that's just coming online. Shown at the bottom is an actual real-life reactor that's been set up in Iceland. It runs on a hydrothermal plant. The energy from the waste energy from the hydrothermal plant is used to drive the carbon dioxide capture, and it's pumped down underground where it's stabilized in mineral form in the underlying basalt. The one that is sitting in between the natural and the technology solutions is the biomass with bioenergy with carbon capture and storage, as Heleen mentioned already. This takes biomass, which in the same way as planting the trees, absorbs CO2 from the atmosphere. So you've got a net flow of carbon dioxide out of the atmosphere into the biomass. You then combust that biomass in order to produce energy. So you've got energy as a byproduct. Instead of letting the CO2 go back into the atmosphere, you capture it and you pump it down. You capture it in the same way as I just described with DAX, with amine or sodium hydroxide reactant to capture the carbon. You then scrub the carbon from that reactant and you pump it down into geological storage. And the last option, which is a sort of technology-based one, but also involves the land, is enhanced weathering or accelerated weathering. A number of rocks over geological time, when they get exposed to the surface, naturally absorb CO2. And this is something that normally occurs over geological time. So CO2 is absorbed by these rocks, such as silicate rocks like olivine or basalt, and they naturally absorb CO2. So if you take those rocks, you mine them, you grind them up, so they've got enhanced surface area, they absorb CO2 more quickly, and then that carbon is mineralized into carbonates. So you grind up the rocks, you spread them on the surface of, for example, farmland and woodland, and there they absorb CO2, and that CO2 is turned into minerals. So this is called enhanced weathering or accelerated weathering. So those are the technologies. This is just a slide just to give you an idea of the potentials. These are maximum technical potentials. So don't pay too much attention to these, because these maximum technical potentials are limited by many barriers. For example, cost, the land that's required, the energy, the water requirements, the non-greenhouse gas effects. But if everything worked perfectly, these are the sort of greenhouse gas removals that you could get if you applied them at global scales. So this technical potential over here is in billions of tons of carbon dioxide. And you can see somewhere between about 1 and 10 gigatons of CO2 per year. But this is a maximum technical potential. And the other thing to note is that there are, as I've mentioned, a bunch of constraints to how these can be applied. So if we look down, we got the costs, we've got costs, energy, the land impact, the water, and the non-CO2 greenhouse gases all play a role. So if a dot is shown in green, it shows that it's, for example, afforestation, reforestation is low cost, low energy requirement, but it does require land. It can increase the water needs, and you can get some other non-CO2 greenhouse gas impacts. Just take BECCS, for example. The cost can be quite high, although it could be lower. It generates a bit of energy, but it uses quite a lot of land and can use quite a lot of water. So what we're looking for is we're looking for technologies that have green all the way across. You can see not many have green all the way across, but perhaps the closest we get is soil carbon restoration, which has low energy costs. It doesn't use any land, it doesn't use any water. You can have some non-greenhouse gas impacts. But that's just a quick whistle-stop tour of the technologies that are available. Again, I have to emphasize that these have a number of constraints and limitations, but I'll hand over to Cameron now to talk in a bit more detail about CCUS.
Thank you so much, Pete, for talking us through these options. Yes, can we please hand over to Cameron?
Thanks, Juliane, and it's a real pleasure to be with you all here today. I'm going to say a few words about how we might use carbon dioxide to generate valuable economic products and how this might perhaps reduce the cost of removing it on a net basis if we can make some good use of it before we lock it away out of the atmosphere. This builds on joint work with a number of colleagues at Oxford, along with me, but also Pete Smith, who you've just heard from. So we'll move to the slides. And the core points, or the three key findings that I want to share with you, is that actually there's quite a number of different ways in which you can actually think of CO2 as a useful input and not just a damaging waste product, which of course it is, damaging pollution, but a useful input into processes that might generate economic value. And we've grouped 10 different pathways in 3 different categories. The 3 categories are cycling pathways. So these are pathways in which you take CO2, you embed it in a product, you use the product, and the CO2 goes straight back out into the atmosphere again in a very short period of time. So the use in producing chemicals or in synthetic fuels or in products from microalgae fit that kind of category. Now, you might think, why bother with a pathway that takes CO2 only to spit it back out again? And it's a fair question. But the answer is, if it stops you from doing something else that would be net emitting CO2, then it might be a good thing. So, for instance, if you can make a carbon neutral fuel by taking CO2 out of the atmosphere, producing the fuel, using it, and then stop digging up petrochemicals and barrels of oil, then that can reduce your emissions. But net, these cycling pathways have limited scope for removals. The second category of pathways is open pathways, where we can use CO2 to produce products. Now here, many of them are the sorts of things that Pete's just covered, so I won't labor the point. But the focus of our work has been on the economic value that you can get from increasing agricultural output from capturing more CO2 and putting it into soil so you can increase crop yields. And as Pete said, that doesn't necessarily move it forever, but it helps, at least in the short to mid-term, decadal kind of timescales to keep CO2 out of the atmosphere, and it buys us some time. And the third category are closed pathways. This is where you're using the CO2 in products and you're locking it up forever. So there's a range of building products where you can actually embody CO2 in them. I mean, most obviously wood for buildings, but also in cement. Cement's currently net emitter of CO2, but you could conceive of a cement which actually sucks CO2 net into it and uses it. As Heleen has mentioned, you can get more oil out of the ground by locking CO2 permanently into those oil wells. It may not necessarily be a good idea on a life cycle basis, but is a use of CO2. Bioenergy based carbon capture and storage is another one, as is enhanced weathering. So potentially getting more agricultural output by putting rocks onto land that take up CO2. So our study looked at these 10 pathways and asked ourselves the question about the economics and the potential to scale. And all 10 of those pathways could conceivably get over 0.5 gigaton of CO2 utilized, not necessarily removed. But Pete alluded to this earlier. Each of them has quite a bunch of challenges, barriers to overcome. And our kind of, we'll lay it out in a minute, but best guess is that in aggregate, you get somewhere between 1 and 10 gigatons a year from these pathways, which is quite a big range at this point, which gives you an indication of the levels of uncertainty. So if I just move along to try and put these pathways into context, here you can see a schematic of the 10 pathways, numbered indeed, 1 to 10. The 3 cycling pathways there are 1, 2, and 3, chemicals, fuels, and microalgal products. 4, 5, and 6, and 7 are all closed pathways, and 8, 9, and 10 are open pathways. So by open, we mean they are storing CO2, but maybe not forever, not a permanent. They could be, you could disrupt the carbon stored, or it could come back after a number of decades. And also on this slide, you get a sense of the scales involved. We've got over 3,000 gigatons of CO2 in the atmosphere at the moment. That's, of course, part of the problem. But that number is very small compared to the amount of CO2 locked up in the soil, or indeed in the biosphere more generally. And it's, of course, tiny compared to the carbon locked up in the lithosphere, in the rocks, in the earth itself, or in the hydrosphere, in the oceans. And that's one of the reasons that these pathways are kind of interesting, because if we could do them at modest tweaks to the flows of CO2 in aggregate, then we could actually really make a material difference. The other thing we did in this paper is to schematically describe all of these pathways according to this sort of figure. So conventional use of fossil fuels, you take the carbon in the lithosphere heat here, and you extract it, pathway K, you get a product, you burn it, and you use it, that's G, and it's just single line from lithosphere to product to atmosphere. But there are lots of other things you can do. You could burn your coal in a power station, you could capture it industrially, and then you could store it. Or you could capture it and transform it to some other product, which might then, might be a synthetic fuel from CO2 from a coal-fired power station, which then gets emitted again on use. And you can start with CO2 in the atmosphere, and you can use direct air capture, as Pete referred to, or you could use the wonders of nature to capture it on land. So all of these pathways can be described in this schematic, and they are indeed described that way in the paper. And let me wrap up by just giving you the kind of crunch point of the analysis, which is to say, how much could we get out and use, how much CO2 could we use by these different pathways, and how much would it cost? So this chart shows you on the horizontal axis the amount of the break-even cost of the utilization of CO2. So where you see a negative number there, it's to say that CO2 utilization to produce these products is already economically effective. Doesn't necessarily mean it's happening at scale, because there might be other non-economic barriers in place, but in some cases it is already happening. And as you can see in a low scenario there on the left, you're looking at maybe a few gigatons of CO2 utilization, which, as I say, could help reduce the cost of CO2 removal. And in a very, very optimistic, everything goes right kind of scenario, you're well above 10 gigatons, and you're pushing 20. But I don't think any of us really, to be honest, see that as a plausible scenario in a context where we're emitting nearly 40 gigatons of CO2 today. But the point to take away, the bottom line is that these sorts of processes, as Helena said, are necessary. CO2 removal is necessary. They can happen at scale, but of course is not going to do the whole problem. So a core message is we have to reduce our emissions significantly at scale and as fast as possible. And what the three of us really are talking about today is a process of mopping up and clearing up the rubbish that's left after we've done what we can. It's not a single silver bullet solution. So that's it from me, and I'm looking forward to the Q&A.
Excellent. Thank you so much. Thank you so much, Cameron. That's great. And we also have Heleen de Coninck here from the University of Eindhoven and Pete Smith from the University of Aberdeen. Discuss this a bit further. So, Heleen, you said for achieving 1.5, there's a choice between faster emission reductions before 2030 and more significant removal after 2030. Do you think, or do any of you think, that it's possible to deliver on the Paris Agreement without carbon dioxide removal at all? Heleen?
So I think what the 1.5 degrees report is concluding is that all pathways, all mitigation pathways have some degree of carbon dioxide removal, and you need it for two things. One is that you will probably, at the moment that you need to be net zero in CO2 emissions, which is roughly around 2050, for 1.5 degree scenarios, and it would be about 2070 for 2 degree scenarios, which is basically, that means you're violating the Paris Agreement, because the Paris Agreement says well below 2. But for those kind of pathways, you probably in 2050 still have some residual CO2 emissions, for instance, for sectors that are hard to decarbonize, like aviation or some industries. And in order to compensate for those emissions, you need carbon dioxide removal. So you need whatever you spend in excess, you need to remove. But there's a second reason, and that relates to the point you just raised. However we exceed our carbon budget right now, because we're not reducing our emissions fast enough, we need to compensate later on in the century. And that determines the depth of carbon dioxide removal that we will be using. So there are two reasons why carbon dioxide removal is needed, and the extent to which is determined very much by how fast we can reduce our emissions now.
Okay. So I think, I get a sense, Pete, Cameron, so I think we're sort of all in agreement that some level of removal is needed. You've talked through a number of options, and I was wondering, what in your view is the most promising technology option or set of complementary options for removal? Helena already made some comments about what is needed. It needs to be ready. It needs to be ready at a certain scale. And Pete, you outlined some of those that have more green dots and less green dots. So Pete, what in your view is the most promising to date?
So I think soil carbon sequestration has a bunch of co-benefits, a whole load of co-benefits, and virtually no downsides. So I think in terms of doing a no regrets option, I think soil carbon sequestration would be definitely something that we can do to remove CO2 from the atmosphere on top of a greenhouse gas emission reduction across all of the sectors. It's not a replacement for conventional abatement or mitigation. So we have to do that, and I would say that's a promising technology. The direct air capture uses a lot of energy, and it's quite high cost at the moment, but those costs are coming down. And I don't think we're not yet able to say which horse we were back at the beginning of the race. I think it's like renewables 20 years ago. We didn't know if wind or solar would work out, or if any of the other technologies that are available would be the best option. But wind and solar are really pushing ahead of other renewable technologies 20 years later. So I think we have to invest in demonstration projects for all of these now. And then some of them will drop by the wayside, and some of them will turn out to be really good, really useful, and the cost will come down. So I think we're not yet in a position to say which is the best. There's some that we can implement now with a no regrets option, because they don't do any harm, they'll only do good. But we have to invest in demonstration projects and upscale them to see which ones are going to work at scale.
Okay, thank you. Cameron, do you want to come in on this, and maybe also on the sort of primary barriers that we're still facing, maybe also looking into the future, what needs to happen in the next 1 to 2 years to get the next 10 years right in terms of the contribution that carbon dioxide removal can make to overall emission reduction?
Yeah, thanks, Juliane. Let me say 3 things. So I think I would actually agree with Pete about the potential of soil carbon sequestration. It's both large and lots of co-benefits. So that's kind of a no-brainer. I'd add to that that some of the forestry and ecosystem regeneration sorts of pathways have significant benefits for nature and biodiversity and other objectives, environmental objectives, and for people actually in mental well-being, while also sequestering CO2, or at least storing it in the biosphere for a period. And it's good to do these things that are kind of win-win-wins effectively. Then on the industrial side, so that's the first point. Second point, on the industrial side, there are a few of these pathways that are already going. I mean, they're already making money. So to highlight 2 in particular, there are companies that I've come across in the course of research for the paper that are already making particular plastics out of CO2, and they're doing it cheaper than you can make it out of a barrel of oil for various reasons, purity and processing issues. And there are companies that are producing aggregates for building materials, and they're making money. They're doing it at they're using toxic waste, in fact, and using CO2 to cure the waste and produce a product at the same time. So these ideas may not be the biggest scale, but they're kind of best in the narrow sense of already making money. And then the third thing I guess I'd say is that the scientific community has been very much focused on BECCS and growing biomass and using it for energy production. And this still, I think, even though it's kind of gone into favor and then out of favor, it still has a big potential. I've just got a slide here to give you a sense of the land areas of the different approaches to taking CO2 out of the air, BECCS and DACCS. This is not my work, it's Felix Kreutzig and his colleagues from last year. And you can see here that, as Pete says, well, DACCS, direct air capture, has very large energy requirements. As he also said, the cost of that energy is plummeting as the cost of renewables falls. BECCS, on the other hand, delivers energy. It's not a net user of energy, it's a net producer, effectively, but it does require some very significant land areas. So to sequester a gigaton of CO2, according to Felix and his colleagues, you're looking at a land area the size of California.
Thank you so much, all. This has been really insightful. Unfortunately, we're already coming to the end of this session, so thank you all very much, and thank you to everyone for joining.
Want access to more CogX videos? Subscribe now for free at cogx.co.